you.
And Judith, can you confirm now that you're seeing my screen?
That's confirmed.
Okay, well, now I will go to the full presentation screen like this. And in principle, now you're seeing the first slide, much as I showed you when we did the test run.
Great, thank you.
Okay, well, look, as Judith said, I've been involved in climate change science since I did my graduate study, in fact, in the United Kingdom. And that was more than 40 years ago now. And what I'm going to try to do in the next 45 minutes is to give a brief overview of climate change science, climate change and its impact, and also focus on the sort of what I would call the critical issues in terms of addressing climate change, both in Australia and globally, recognizing, and I'm going to start by actually going to a slightly better pointer, if I can get it to work. Here we go. And I'm going to focus to start with on the graphic on the left-hand side of this first slide, which shows global average temperatures from 1850, way back over here, right up to 2023. And this latest set of data was only released in January. And these are global average temperature departures from normal, where normal here is the pre-industrial period, the 1850 to 1900 period. And the data is the global average from both land surface temperatures or air temperatures over land, collected from weather station data, from weather services all around the world, and ocean temperatures collected from ship data, as well as most recently satellite data. And if you look at this, you'll see, first of all, that the temperature in the most recent year in 2023 was about 1.4 degrees above the pre-industrial levels back here. There's been a very pronounced warming from 1900 right up till the present. Not every year is hotter than the previous years. There's lots of year-to-year variations, but the long-term warming trend is very clear to see. And the reason I've focused here on 1 degree Celsius above pre-industrial and 1.5 degrees here is that the international target for trying to limit global warming at a safe level for humanity and for ecosystems all around the world was agreed in 2015 in Paris to try to limit global warming to less than 1.5 degrees above pre-industrial levels. The only problem is that, well, one of the many problems is that for the first time in the last 150 years, we have had a 12-month period from February of 2023 to January of 2024. The last 12-month period was already above 1.5 degrees above pre-industrial levels. Now, climate is not the month-to-month or year-to-year variations. Climate is defined to be 20 or 30-year averages. So we'll have to wait another 20 years to see, in fact, if we exceed this target level of limiting global warming to below 1.5 degrees, but it is actually already virtually certain that we're going to exceed 1.5 degrees of global warming relative to the pre-industrial period in the next 20 years or the coming 20 years. Now, I'm going to focus not on the graphic here, but use the science report from the Intergovernmental Panel on Climate Change that was released in 2021 and talk a little bit more about that. And here's some views of leaders. And Antonio Guterres is the UN Secretary General. When this report came out, the science report from the Intergovernmental Panel on Climate Change came out in 2021, he said it is a code red for humanity. By that, he meant we need to stop and we need emergency action. But Andrew Mackenzie has given what I think is a very good, concise summary of the climate change science. He was at the time Chief Executive Officer of BHP. So this is in fact a sort of business or industry mining company perspective on climate change. He wasn't trying to hide it. His summary is this 4 lines. The evidence is abundant. Global warming is indisputable. The planet will survive. Now, he didn't say that there's other things that humanity could do to destroy the planet, like unmitigated nuclear warfare could destroy the planet. But he was then talking about many species may not survive when he's talking about ecosystems. He didn't say that many people may not survive, nor did he not say that many businesses will not survive, but they will be part of my conclusions at the end as well. So now let me go to the next slide. And what I'm going to do is give a brief overview of what the Intergovernmental Panel on Climate Change is, because some of you will not know or won't have heard about this Intergovernmental Panel on Climate Change. It's often abbreviated to an acronym, the IPCC. And this group was established in 1988. Its role is to assess the scientific, technical and socio-economic information that's relevant to understanding the risks of human-induced climate change, the impacts of human-induced climate change, not only now, but for the next 100 years, and then options for adaptation to the impacts or reducing the magnitude of human-caused climate change. Now, it's important to understand 2 things. First of all, the members of the IPCC are not scientists, although scientists and experts write the report. The members of the Intergovernmental Panel on Climate Change are governments with one representative from each government who is the representative of that government on the Intergovernmental Panel on Climate Change. So there's about 150 or 160 members available to vote. And all the reports are approved by consensus. But consensus for the IPCC means unanimously. Every country approves all of the reports and approves word by word the summaries. I'm going to be using some of one of the summaries, the summary for all from this most recent report. As I said, the IPCC was established in 1988. Its first report came out in 1990, and the most recent report came out in 4 volumes. And if you wish, you can download every page and every word from the 4 volumes. They're publicly available on the IPCC website, and there's a link to the website in the references at the end, but I don't recommend you downloading it because it's more than 6,000 pages long across the 4 volumes, and they're in 10-point font. So you can access it. All the figures are publicly available, but look, no one, not even myself, has bothered to read even the most recent report. I search for material that's most relevant for my interests, and particularly focus on what's called the summaries for policymakers, and I'll be showing some of that material. Sorry about that. My phone was not on silent. It is now. Let me get back to what I was saying. What the IPCC has been trying to do, and I've got a very interesting and amusing graphic at the end, is to prepare these assessment reports. The first one, as I said, was in 1990. We're up to the 6th assessment report. over those 30 years, they've been coming out about once every 5 to 7 years. The first one, it was in 1990. The second one was in 1995. Then they got a bit further apart. The third one was in 2001, moving to 6 years apart. And then most recently, the most recent assessment report was nearly 7 years or 8 years from the previous one. The requirement is that these reports must be neutral. They cannot make recommendations. They can make conclusions about the science, but they do not make recommendations. They provide an assessment. And what is critically important in the assessment reports is that they involve a multi-stage review by independent experts and by governments. And if you wish, you can request to gain access to the review documents. Every single comment is archived, made available to anyone who requests it. But there's another 6,000 pages of review comments associated with the different volumes and the responses from the authors. And so the reports themselves are written by independent experts. They have to respond to all the review comments. Governments also get an opportunity to provide review comments, but they are essentially assessed by the experts, and then the reports get finalized at a plenary meeting and approved by all the governments. So that's more than enough, but it is the best available scientific assessment, and it is recognized as that because more than, a number of other, if you like, science assessment processes, not just for climate change, but biodiversity loss and other processes have followed the same sort of process. It's been reviewed over and over again. It is still considered the best available solution approach. So what I'm going to do now is quickly move on to the science. As you will tell, I've spent too much time right at the beginning talking about the background. We started a few minutes late. I will give plenty of time for, if you like, conclusions. The really interesting thing is that for most of human civilization development over the last 20,000 years, the period since the end of the last ice age, which finished 20,000 years ago, we've had a relatively stable climate. What that means is that the incoming energy from the sun, the sunlight that heats up the surface of the earth, heats up the oceans and the land masses, that generates heat, and that heat radiation, or what's called infrared radiation, gets emitted out to space. And the reason that we've had a relatively stable climate is there's been a long-term balance between the outgoing radiation from the surface of the earth and from the atmosphere out to space and the incoming solar radiation, as well as the reflected solar radiation from clouds and things like that. But there's been an overall long-term balance. Now, it's really important now for me to recognize that the Australian First Nations people, or Indigenous people, Aboriginal and Torres Strait Islanders, are the only continuous Indigenous civilization that has survived the transition from the last ice age to the current period. Indigenous communities in Australia have managed country sustainably through the last ice age to the current interglacial period, and all of us can learn from managing country by the Indigenous communities over that period. Sea level rose more than 100 meters, and the First Nations stories and songlines tell about the massive sea level rise along Australia's coastlines and the changes in water resources and changes on country. So we can still learn how they managed the 5 degrees of global warming from the last ice age that finished 20,000 years ago to the present period. Because, unfortunately, we may still have to manage another 4 degrees of global warming from the current era to the end of the 21st century. And I'll talk more about that in a minute. But what we know now is by emitting more greenhouse gases into the atmosphere, while there is still essentially the same amount of sunlight coming in, the extra greenhouse gases prevent the loss of some of this outgoing energy. Greenhouse gases trap some of the outgoing infrared radiation, and the extra heat that's then gained in the oceans, primarily the land surface and the atmosphere, they're heating up. And they're heating up because there's less outgoing infrared radiation because of the increase in greenhouse gases. That's what the enhanced greenhouse effect is that we're experiencing. There's lots and lots of evidence. I'm happy to talk more about this later on. But now let's look at how do we know, first of all, that this increase in greenhouse gases is due to human activity. Well, here's a graphic from the last 1,000 years of carbon dioxide concentrations. These dots here that are basically horizontal show the carbon dioxide concentration in the atmosphere from small bubbles of air trapped in ice cores in Antarctica. And those ice cores are extracted. We can actually go back 800,000 years in ice cores from Antarctica and extract the air trapped in the bubbles. And what we see in this air trapped in the ice cores is there's been a very rapid growth of carbon dioxide from the ice cores. And when we match that with the more recent observations of carbon dioxide from Cape Grim in Tasmania, we see it matches very well. The only problem is that we're now at more than 415 parts per million of carbon dioxide in 2023 at Cape Grim. Now, that just shows that the increase since the pre-industrial period, since the Industrial Revolution, is very dramatic. But it doesn't show that it's due to human activity. And in fact, one of the scientists, the earth scientist and mining director or mining company director now, who was formerly at the University of Melbourne, says, well, this is just due to underwater volcanoes. And the reason he says it's underwater volcanoes is we see volcanoes, they do emit carbon dioxide, but they've got to be underwater because we would see if there were lots of eruptions, and there aren't. And this is not due to a massive increase in eruptions. But let's look at this other graphic, and the mirror image graphic up here, which shows what I would call a very rapid decline, is in fact the ratio of the carbon-13 isotope of carbon dioxide to the carbon-12 isotope. And some of you, if you remember back to high school science classes, carbon, the most common isotope, has an atomic weight of 12. But there is, in fact, another stable carbon isotope with an atomic weight of 13. When carbon dioxide is taken up in plants through photosynthesis, it preferentially takes up the carbon-12 isotope. Fossil fuels are fossilized plant material, and if we burn fossil fuels, it preferentially releases carbon-12 carbon dioxide. And exactly the same thing happens with land use change. If you chop down trees to make more farming land, or if you chop down trees, as happened since the Industrial Revolution, to grow more crops, to have pasture land for animals, then you end up leading to also more release of photosynthetically processed carbon dioxide. That means we get more carbon-12 and less carbon-13 in the carbon dioxide that's released, and it shows with 100% certainty that the increase in carbon dioxide is due to burning fossil fuels and land use change, both due to human activity. There is no doubt that the increase in carbon dioxide in the atmosphere from the pre-industrial period to now is due to human activity. Not primarily, it's due to human activity. So, no doubt. Well, what about the temperature change? Well, let's look over an even longer period. This is a graphic. First of all, the same as I showed before. This is the observational data from 1850 right up to the present. And what you see is the 1.1 or 1.2 degrees of global warming when you look at decadal averages, not just the 2023 temperature, which is much higher up here. That's only a one-year temperature. When you look at the decade-to-decade variations, it's only 1.1 or 1.2 degrees above the long-term pre-industrial average. But if in fact you go back to essentially 1 AD, it actually was warmer. And in fact, you can see the year-to-year and decade-to-decade variations, quite uncertain, but there weren't any thermometers. How do we see these decade-to-decade variations? Well, you have to collect data from different regions around the world using what's called proxy observations, tree rings, ice cores, stalactites and stalagmites in caves, coral records. You can combine all of those together. And what you see is that actually that period, the Roman era, was relatively warmer than the period from 1500 to about 1850. And then since 1850 or since 1900, there's been this very pronounced warming. And in fact, the most recent decade temperatures are unprecedented for at least the last 2,000 years. So the 1.2 degrees or 1.1 degree of warming that we've seen is hotter, means it's hotter now than at least the last 2,000 years, and probably hotter than at any time since the last interglacial, which was more than 100,000 years ago. And which of the factors have contributed to this? Well, it's the increase in carbon dioxide, as well as some of the other long-lived greenhouse gases have contributed to the warming. But there are some factors that would have contributed to a cooling or offset some of the warming. And in fact, some of those factors include increases in air pollution from different sources, like nitrogen oxides from pollution from cars, or sulfur dioxide from burning coal in coal-fired power stations, as well as in other industrial activity. So we haven't seen all the warming due to the gases in the atmosphere. Let me move on. I've spent too long on those. What is the temperature variations that we've seen in Australia when we look at the last decadal average? Well, this graphic is showing a slightly different set of data. It shows the temperatures year by year across Australia, averaged across the whole of Australia in this ragged line up and down. And the smooth line here for the period from 1910 right up to 2010 shows the running 20-year average. And it finishes at 2010 because it's the average from 2001 right up till 2019. And in fact, well, actually it's right up till 2021, that's right, because here is 2019, and 2019 was the hottest year across Australia. And if we look at these variations, and these are again shown as relative to the pre-industrial period, the 1850 to 1900 period, we see that temperatures in Australia are about 1.4 or 1.5 degrees relative to the pre-industrial average. So it's really interesting. Australia is hotter, warming up faster than the global average. Now, this is my question to you, and you've got to think about the answer, but I will tell you, and someone can ask this question at the end in the Q&A period, but the answer is most people are not fish. And that will help you think about the answer, but let me leave you with the intelligible, not stupid answer, although I still think that most people are not fish is a sensible answer. You've just got to ask the right question. And so I will give that answer right at the end. But the really interesting thing is that, as I said, 2019 was the hottest year in Australia, but this is the projections of the year-to-year temperature variations out into the future. And this is climate model simulations of the year-to-year and decade-to-decade temperature variations. And if you look at the decade-to-decade temperature variations from 1910 right up till 2010, there is a very good agreement. You can't explain the observed warming unless you take into account the increases in greenhouse gases in the atmosphere. And this is using more than 50 different global climate models run across the whole planet and just extracting the temperatures over Australia and averaging them decade by decade. We can do exactly the same thing into the future. And unfortunately, when we look at future temperatures, first of all, when the global temperatures reach 1.5 degrees, we're going to see Australian average temperatures reach 2.25 degrees or thereabouts. And when the global average temperature reaches 2 degrees up here, Australian average temperatures will be just about 3 degrees. So Australian temperatures are warming up about 40% higher than the global average. And in fact, when we get to the 2040 period, 2021 to 2040, this decade here, the average temperature in 2019, that record black summer temperatures and the record for the whole of 2019, is exactly what we're going to experience every year, more or less, in 2021 to 2040, which is a very unpleasant scenario because if we get a hot and dry year, it'll be much hotter than 2019 was. So let me talk about that more now, about what we've experienced already and what we're going to experience likely in the future. And I've talked about temperatures, but in fact, there have also been significant rainfall changes. And I'm going to look first of all at wintertime rainfall changes. And it's really interesting. The north coast of New South Wales and many other parts of the southeast of Australia are showing red colours, and the red and orange colours mean declines in rainfall, much below average and lowest on record for the reds. And so much of the southwest of Australia and the southeast of Australia has been drying in the cool season. And some of you may have experienced that in your gardens. Cool season rainfall has significantly declined over the last 50 and 60 years. But if you go to the warm season, the October to April rainfall, you get rather different circumstances, particularly in much of northern Australia. And what we find across much of northern Australia is that the wet season rainfall has increased in much of North Queensland and much of Western Australia, and the changes there's only a small number of places, not much rainfall increase in the North Coast region of New South Wales. Victoria has actually had a slight decline in rainfall, and there's spotty changes in much of the other parts of southeast Queensland and places like that. So let me now go to say, well, okay, what can we expect in the future? And I need to speed up a little bit. Well, if we want to look at possibilities of the future, if you like, you can go to find a crystal ball. It works very well, but I don't trust crystal balls. I could go to an economist and ask him, well, what's going to happen to greenhouse gas emissions? And I'm not very confident in economic projections of greenhouse gas emissions. But what has been done is to look at a range of different scenarios. And these are scenarios of carbon dioxide emissions from 2015 right out to 2100, looking at a range of different economic and, if you like, social and industrial developments. And these look at scenarios for very low emissions, where, for instance, emissions stop in, or were supposed to stop in 2020, or start reducing in 2020, fall to zero soon around 2050, and then other scenarios like this one here, where emissions just continue to grow. Later on, I'll be talking about two different sets of emissions, primarily this one and these two down here, because the global warming target, remember I said that countries all around the world have agreed to try to limit global warming to 1.5 degrees. Unfortunately, this scenario that gets to zero emissions in 2050 is the only one that limits global warming to about 1.5 degrees. And this one, based on all current commitments by all countries around the world, only limits global warming to 2.8 or nearly 3 degrees. Remember, 2 degrees of global warming here was 3 degrees in Australia. 3 degrees of global warming would be 4 to 4.5 degrees across Australia. So what do those emission scenarios mean for the future? Well, this is the average temperature projections for those different emission scenarios. Here is that very low emission scenario. Temperatures peak at just over 1.5 degrees around 2050, and it's only if we can reduce emissions to below zero by 2050 and then start to suck carbon dioxide out of the atmosphere that the temperature will start to cool rapidly and get back to 1.5 degrees. So what I'm going to do now is just go back a little bit. Let's look at that scenario again. Well, here we've got 40 billion tons of carbon dioxide being emitted. In this one that gets back to 1.5 degrees, we're actually sucking, through human activity, 10 billion tons of carbon dioxide out of the atmosphere every year. And without that, we're going to exceed 1.5 degrees. So let's look at some of these other scenarios. Well, this was once called the business as usual scenario. It has unheard of. No humans have experienced any of these scenarios. Remember, we're now experiencing global average temperatures that have been not experienced for the last 1,000, 2,000 years. So we're already experiencing temperatures that are unprecedented for 2,000 years, and temperatures like this would be unprecedented for 100,000 years or more. So what are the impacts? Well, I'm just going to summarize the impact by looking at global impacts across all land areas and looking at extremes, a few graphics. So these are in 4 different columns. The sort of the 1.1 degrees of warming, which was today, essentially the last 10 to 20 years. 1.5 degrees of warming, which will be the 2030s to 2040s. 2 degrees of warming, which will be roughly 2050. 4 degrees of warming. We don't want that to happen, but this is what happens. So this is the hottest temperature of any day in a decade, averaged across all land masses. And notice the land temperature maximum averaged over the whole planet, over all the land masses, is hotter than the global average. As I said, Australian temperatures are hotter. What happens when we get to 1.5 degrees? Well, we actually get nearly 2 degrees for the hottest day in the year. We get to 2 degrees of global warming, we're getting to 2.6 degrees. and 4 degrees of global warming, 5 degrees. But let's look at rainfall extremes, where this is now looking at the wettest day. And this is the change in the wettest day in a decade compared with the pre-industrial period. And already we're seeing an increase in the wettest day relative to what it was in pre-industrial time. But that continues to increase. It increases even more, so that in the 2030s, we're going to expect a further increase in the wettest day in the year in any decade, and even increase even more for each increment in global warming. The one thing we do notice is that actually snow cover, which, to be honest, there's not much snow in the north coast of New South Wales, but there is in the Kosciuszko region in the Snowy Mountains, and there's pronounced decline in snow cover and snow extent in the Snowy Mountains and in all mountainous areas that experience snow. Pronounced reductions in snow cover. There are increases in the intensity of tropical cyclones in all areas projected as well, but actually a reduction in the total number of cyclones. It's just that the ones that occur are likely to be more intense. Okay, what are we finding now if we just focus on the New South Wales north coast? And pretty well this map, very small scale, is where you're sitting, maybe a little bit closer to the coastline, but it doesn't show up very well. This is a summary that I have extracted from a report from ADAPT New South Wales released a year ago, which was for projections of climate change in the New South Wales North Coast. What it's already looking at is what's happened to hot days and cold days. They've already shown that hot days are increasing, cold nights are decreasing. And then it looks at 2 different periods into the future. The near future, the next 15 years or so, and the far future, essentially centered on the 2070s. And what we expect is, again, maximum temperatures to increase, minimum temperatures to increase, and cold extremes to decline significantly. What is expected for the mean rainfall is increases in mean rainfall in the autumn and in spring, but declines in the wintertime, which is much like what we've seen already. And the increases in temperatures, the increases in drought, particularly in spring and summertime associated with the hotter temperatures, and the decline in wintertime rainfall all lead to significant increases in fire danger and fire weather in both springtime and in summer. And that's exactly what was experienced in 2019, but many other years as well. Over the last 30 years, there's been substantial increases in fire intensity. I've added in these 2 extra summary points because they weren't included in this graphic from ADAPT New South Wales, but they show up on the next one that I'll show. First of all, extreme rainfall is expected to increase globally, but also in northern New South Wales. And this is the 1-hour rainfall and the 1-day rainfall. And that's exactly what you've experienced already with extreme rainfall and flooding in the Clarence River, in Lismore, over the last 4 years, and even this year, in 2023, even though an El Nino had been forecast and did occur, there was extreme rainfall again, leading to lots of flooding. And there's also been pronounced erosion along much of the New South Wales coast, leading to loss of beach extent and increases in sea level extremes. And sea level will continue to rise by 27 centimetres by mid-century, and it will continue to rise for at least the next 300 years, just due to the warming we've experienced already. Okay, this is another graphic that I thought might show some of the impacts in different regions. Let's start up here on the top left-hand corner, looking at ecosystems like the rainforest regions in the New South Wales coasts, up in the mountain areas. What we know is that the drier conditions in winter, together with the hotter conditions, is leading to dramatic increases in bushfires, such as occurred in 2019, with unprecedented bushfires affecting the World Heritage areas and affecting ecosystems everywhere. What we know is that drought occurrence is increasing in some seasons, and what that means, together with the increases in temperature, is that cropping and some species of cattle are going to need to change to adapt to the hotter temperatures and the changes in rainfall. Let me look at the ocean areas. And yes, the ocean areas are also affected. While we talk about hot extremes for affecting people and ecosystems, there are also heat waves in the ocean, and those ocean heat waves are affecting the seaweed and many ocean critters. And so the East Australian current that flows southward from Queensland across the New South Wales coast down to Tasmania is now bringing warmer water along the New South Wales coast, and with it, different species of fish, as well as different species of pests and new diseases. But ocean acidification, due to the increases in carbon dioxide, is also affecting the sorts of species, marine creatures that we get in the oceans. And the carbon dioxide increases in the atmosphere also lead to increases in ocean acidity. Finally, for coastal settlements, whether it's the sea change people who want to look over the oceans, or infrastructure developments, tourism, sea level rise and storms are causing major impacts on the beaches, but also all of the infrastructure on the coastlines as well, and it will get dramatically worse. So I've talked about what is needed to stabilize emissions. I've talked about impact of climate change globally and in the northern New South Wales. So what do we need to do to limit global warming? Well, we need to reduce Australia's emissions, and Australia has made a commitment under the current government to limit global warming by 43% by 2030 and to reach net zero emissions in Australia by 2050, which the government argues is consistent with the Paris Agreement and the commitments like that very low emission scenario, which, remember, I said achieve net zero emissions by 2050. So how are we going? This looks at historical emissions in 2005 and 2020. This is Australia's emissions projections released by the federal government, the Department of Climate Change, Energy, Environment and Water. And this was released in 2023. So it doesn't have 2025 data yet, but the projections are pretty stable for that. If we look at this and projections to 2030, the only area where there has been significant emission reductions is in the electricity generation sector, because lots of people have been putting solar panels, and wind turbines are now providing electricity rather than coal-fired electricity. Coal-fired power stations are being phased out. But it's interesting, industrial energy for production of iron and steel or for other sources actually has grown over the last 20 years. transport-related emissions from driving cars, trucks, diesel vehicles, or trains has also grown dramatically. Almost every area, agricultural emissions dropped a little bit, but that's primarily because of the drought in 2020 and will actually regrow a little bit by 2030s. The only other area that's fallen is the drop in land clearing associated with agricultural growth. And so land clearing has shifted from an emission source to a negative emission source because of forestry and planting more trees. So let's look at the total. Let's look at 2030. The total in 2005 was just over 600. Now, it's relatively easy to look at 40%. 40% of 600, well, let's multiply by 6 by 4 would be 240 million tons of emissions. We'll take 240 from 616. Remember, the target should be 43%, but it's easier to use round numbers like 40%. 240 taken off 616. I'm not going to ask you that. I'll do that in my head. It is 300. Let me get it right. It's 376. 240 subtracted off 616 is 376. We should be lower than that because it's 43%. So we should be looking at 250 off that. But look, both of those, the projections from the Australian government is we're not even going to achieve. We need stronger emission action, and that's achieved in 2035, but we need even stronger action to achieve zero emissions by 2050. If you look at what we've achieved up to here, this is about 50% in 30 years, from 2005 to 2035. But we've got to get to zero emissions by 2050. We need another 50% in 15 years. That requires much, much stronger action across all of these areas. You can't achieve zero emissions unless we reduce it in transport, in agriculture, in waste, in electricity, and industrial activity. Good luck. So what do we need to do? We need to use electricity and other energy sources more efficiently. We need to manage our energy use as much as we can, and you will save money if you use energy more efficiently. You need new appliances, new vehicles that use less petrol, that use less electricity. We also need to switch to zero carbon energy sources like wind power or solar power or tidal power that use renewable energy and generate electricity. We have to phase out fossil fuel use completely. You need to use electricity for everything. No petrol in cars, no diesel in cars. You can use electricity in EVs, or you can use, in the near future, hydrogen as well. In addition, we need to increase carbon sinks. We need to manage forests, plant more forests, stop deforestation, and manage all our native forests. That will capture carbon dioxide from the atmosphere, and we can then progress. We also need to recognize that everything we do, everything we buy, unless we grow things ourselves, food stocks, everything we buy is being produced using fossil fuels to either produce it and transport it, or if it's local, you need to think about how far it's traveled before you use it or consume it. Living locally, eating locally, and buying locally, local products is much better This will require behavioural changes, and the whole Australian economy, as well as the whole global economy, is in the process of changing. So let me finish. I said before several times, the human influence on the climate system is clear. We see the human influence on the carbon dioxide emissions, and those carbon dioxide emissions then lead to increases in global temperatures and Australian temperatures. The more we disrupt our climate, the more will be the impact on people, on ecosystems, on our agriculture, on our plants and all our animals and native species, as well as on our coastline. We know how to fix the problem. It's not new. We have known that we can power Australia and power the world by renewable energy for more than 10 years. And I should point out, although you can't see it here, this summary slide was from the previous IPCC assessment in 2013, a decade ago. We have known about this problem. We also know that every ton of carbon dioxide emissions adds to global warming, and every ton that we don't emit, that we stop using fossil fuels, means that we don't get as much warming globally. Now, there's one other critical aspect that I should have talked about here on this slide. Yes, this is Australia's emissions in 2025, 450 million tonnes of greenhouse gas emissions. Unfortunately, Australia is a massive exporter of coal and fossil gas. And even though those aren't counted in these emissions, the emissions when that coal and gas is used in another country, overseas somewhere, whether it's China or Japan or India or Indonesia, when it's burned, those emissions lead to double Australia's emissions, and more than double. So it leads to more than 1,000 million tonnes of additional greenhouse gases. That is Australia's responsibility. And yet we have no plan to limit the export of coal and fossil gas. That's another important conclusion for Australia. If we don't stop that export, global warming will continue, and we'll get much more than 3 degrees of global warming. So I've given a summary of the science. Judith liked this summary graphic because it talks about the IPCC assessment reports starting in 1990 with a one-line conclusion. Essentially, not absolutely certain, but this climate change thing could be a problem. 1995 conclusion, yes, climate change is definitely a problem. I was first involved in the IPCC assessments as an author in 1995, and then as a coordinating lead author, leading a chapter in 2001. Yep, we should really be getting on and sorting this thing out really soon, because increases in greenhouse gases have contributed most of the warming from 1900 to 2000, most of the global warming. 2007, the next assessment, the fourth assessment report. Sounds like a broken record, but yes, we really do have a problem. Yes, we've checked everything, and exactly the same in 2013. It needs action. And then this cartoon, you can't read it here, came out in 2013. So this was the anticipation. This is a little bit like the Secretary General of the United Nations saying code red for humanity. It's not this saying, it's 2019 and the scientist asking, is the microphone actually working and is anyone listening? It's pretty clear that Donald Trump is not listening. And in fact, it's also pretty clear that the former Liberal National Party government, which phased out any emission reduction activity in Australia is also not listening to the science on climate change, which says we need much stronger action if we're to limit global warming to 1.5 degrees. There is a final slide that's got lots of references. Don't look. I'm going to stop sharing now and go over. We're going to have a break now, I think, Judith. I've stopped sharing and hopefully, well, let's take a quick break and I'll come back and we'll have question and answer time. And you can put the lights back on in the building.
Okay, thank you very much. So we'll be back in 10 minutes. Thank you.